Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of C++ Crash Course, we're going to go over some of the modifiers that may not have been covered in other videos or may not have been covered enough in other videos. So let's get started. So we'll start this out by opening up our example, which will be called modifier deepdive.cpp. And so what we're going to go over first is static, right? So what does static do when we have it before a variable? So in this case, we have static inside of a function called static count. So every time we call this function, let's think about what happens, without the static modifier. So let's pretend we don't have static here. So what would happen is we call the function int. We get a temporary variable called count. We set it equal to 0. We print count, and then we go ahead and increment count. And then immediately after that, the function finishes. Count goes out of scope, so it gets kind of released. And then, the next time this function gets called again, count's going to be, we're going to get a new count. We're going to set it equal to 0, and we'll go ahead and print out again. So this should only print 0 in the case that we're familiar with. So what happens when we have static count? So what happens when we have static count is we, oh, there we go. What happens when we have static count is we get some kind of persistence between function calls. So this count isn't going to just go out of scope and be released at the end of the function. It'll actually stick around for every time we call this function. So in this case, what will happen is we'll initialize it once, then every single time, count will get incremented by 1. So what we'll see is count will monotonically increase. So at first it will be 0, then it will be 1, then it will be 2, then it will be 3. So this initialization really only happens once, right? So it's not going to set it to 0 every single time. And so we'll see that down here in our main function. So we'll just call this static count 5 times in this for loop. And what we'll see is that that variable that's static will just count up every single time. So that's really static. So this isn't only for functions. You can have static inside of classes as well if you want things to be persistent between classes. Okay, so that's going to be the static modifier. So let's talk about next with this simple class called flag class. Let's talk about mutable and const. So we've gone over const before, as we've seen, it stands for constant. So it basically means that things aren't going to change, kind of like how it implies. So if we have a method like this, or even a function that's constant, so in this case, it returns a Boolean value, and then if we have it, so after the function name or method name and the parameter list, we have const. This just says that this method isn't going to modify any of the fields inside of this object. And then, even down here, we could create a new object that's constant, and that says that you're not allowed to modify any of the fields within this object. So, there may be cases where we want to say have a constant object, but there may be a specific field in the object that we don't want to be constant. So in this case, we might want to track the number of accesses that we have to an object. So we can have mutable to get around this. So when we declare something as mutable, that's basically saying, hey, I know that maybe this is a constant method, but we're going to give you special permissions to be modified. So down here, we're actually incrementing accesses, right? So if we actually get rid of mutable right here, so if we delete it and we save the file, we see that I get a little double red arrow here, and it actually gives me the error down here. It says increment of member flag class accesses in read-only object. So it's saying that I'm going to fail here, or the compiler is going to fail here because I'm trying to change something that's read-only, right? So we'll go ahead and put mutable back, and we'll see that it goes away. And likewise, so this bool flag, it shouldn't be changed inside of this constant method. So if I go ahead and do, say, flag is equal to true, we'll see a similar type error where, except this time it says assignment of member in read-only object. So mutable allows us to get around this constant modifier. Okay, so that's going to be constant, and for the example for this, we're just going to create a simple object, flag class, with just a flag is equal to true, and then we'll go ahead and call that getFlag method 5 times, and then we'll print it out every single time. And what we'll just see is accesses will increase, so even though this is, say, a constant instantiation of that object, and we're using a constant method, we can still modify that value or that field within the object because it's mutable. So the last thing we want to talk about is volatile. So volatile is a little bit trickier because we're really thinking, when we're using volatile, we're generally thinking about things outside of our code. And we're thinking about how the compiler is going to treat our code. So in this case, we'll declare two integers, one volatile and one not, and both of them will execute the same loop. So one of them will be in this loop that just says, you're going to go 16 times, and I'm going to multiply you by 2 every single time. So this is essentially just calculating 2 to the 16, which is 65,536. And so the volatile version will do the same. So volatile as a keyword tells the compiler, I don't want you to optimize this variable away, right? So it limits what the compiler can do with that variable. And so we'll see what that looks like when we look at the actual assembly. But let's go ahead and look at the other two examples first. So we'll do G++-O on modifier deep dive. And then we'll go ahead and enable the highest level of optimization, which we can do with -O3. If we want to know optimizations, we could do -O0. Okay, so let's go ahead and run our code. So here's /modifier deep dive. So here we see that count that was static is persistent between function calls inside of that loop. And so it just counts up, right? So it doesn't get reinitialized to 0 every single time, as if it wasn't static, we would just see count equals 0 printed 5 times. Then we see that even though we've got a constant method, we can change a field inside of that object even though that it's constant. So here we see axes be incremented from to 1 to 2 to 3 to 4 to 5. And then finally, rather boringly, we see that those two loops calculate exactly what we expect. But like I said, this is more of something that deals with the compiler, so we have to actually look at the assembly that was generated to understand this. So let's go ahead and get that. So we can get the assembly for a binary by doing object dump -d for disassemble on modifier deep dive, and I'll go ahead and put this in a file called out.asm. So let's go ahead and open up out.asm, right? And so, here's our code, right? So it's called modifier deep dive. It's our executable name, and it's x86-64 instructions. So there is a concept of kind of a main function still here, so we can find this label of main right here. And then what we really care about is at the very bottom, right? Or what we expect it to be at the very bottom for printing out our two things, being our two values. And we can even get some kind of insight into that we're printing out here. So we see that we've got some kind of call to some O stream, so some output stream. And we see over here, we even see cout. So you're going to see some mangled names here, and that's just an artifact of compilation, but you can still kind of glean what's going on. And so, these are going to be, these 4 right here are going to be our output prints at the very end of the program, or rather the O stream ones are going to be related to our output prints at the end of the program. So, when we're looking for for loops inside of assembly code, what we're generally looking for is some kind of comparison, and then we're looking at some kind of jump instruction that is based upon that comparison. So, near the end of the program, we do see, say, a jump instruction here, but this really doesn't have anything related to this volatile. So, what we're really concerned about, it's a bit hard if you're not familiar with x86 instructions, and believe me, I'm not terribly familiar, but I've got enough knowledge about assembly language to kind of understand what's going on here. But if we look at the very bottom, we can start working our way back based upon where the prints are. So we'll look at the first print, right? So the first print should print out our non-volatile version. And we see something interesting here. We see this immediate value, right? And so whenever we see an immediate value, that we can generally trace that back to some kind of assignment at some point. Otherwise, we'd be loading a value from memory. So we see this value 0x10000. So this is actually 65,536. And so the first thing we should think is, well, that's odd. That's the exact value that I was expecting to calculate. So why do I see it in the assembly code before the program is even run? Well, this requires us to kind of look back at our code itself. So the compiler knows exactly what this non-volatile is starting at, which is the value of 1. It knows exactly how many loop iterations it will take, 16, and it knows what it's doing every loop iteration, multiplying it by 2. So compilers are pretty darn smart. So the compiler said, well, I could do this loop for you, or I could just give you the value, right? So I can tell you what this value is going to be ahead of time. I know it's going to be 65,536. So when you want to print out that value, instead of calculating it, at runtime, here, just go ahead and print out that value, and I'll hand it to you and put it in the instructions. And so that's exactly what this right here. So it completely optimized away that variable and that entire loop. Okay, so let's see what it does with the second print. And so we see something similar right here. So this is a move of an immediate value into some register ESI. And then over here we see something different. We see a move into ESI, but it's not an immediate value. It's this memory location with an offset. So 0xc, so 0x is just a prefix for, it just says that whatever's after 0x is going to be a hexadecimal number. So some 0xc offset from whatever's in the register RSP. And so we can actually trace back RSP a little bit, and we see that RSP corresponds to this big long line of instructions that seem to be doing the same thing over and over and over. So while Volatile tells the compiler and limits the compiler at getting rid of a variable, it's not going to completely take away all optimizations. So if we know exactly how many times we're going to do a loop, there's no real point of doing a comparison check every iteration of the loop. So let's say I wanted to count, a number 5 times. Let's say I wanted to add, I had a variable a, and I wanted to add 1 to a 5 times. So I could do that in a loop and have a is equal to a plus 1, and then have a for loop. Or the compiler can just optimize that away and just say, put 5 add instructions in a row maybe, and do a is equal to a plus 1, a is equal to a plus 1, a is equal to a plus 1. And this gets rid of an instruction for doing a comparison, and it also gets rid of an instruction for doing a jump to the top of the loop. So it can still do those kind of optimizations. But what we see here is that every time we want to do an add, we have to load the value from memory, do the add, and then we have to store the value to memory. So it can't just get rid of this variable and pre-compute it for us. So, that's the real difference here between using volatile and non-volatile. Volatile will keep the compiler from optimizing things away. And you may be wondering, why do I care about this? It seems like if the optimizer can optimize it away, that's a good thing. And in a lot of cases it is, but in some cases it will completely ruin your program, and your program will not function. And one of these is when you're doing stuff with memory mapped I/O. So with memory mapped I/O, you have something in memory that gets mapped to some peripheral device, or some device that also has access to this. We have a piece of memory that's not for storing values, but it's a way of communicating with the device. So, compilers really think upon, just what this thread of this CPU program is doing. So it's not expecting some I/O device, to be changing things in memory. So, if we had a loop that say is polling on a certain value, so maybe you set a value equal to something that's from some piece of memory mapped I/O, and then you say while that value is not equal to 1, the compiler might be try to be clever and say, okay, well, you assign that value at the beginning, and then you never do anything with that value again. So I'm just going to assume that you wanted an infinite loop. So it might completely remove that variable and just say while true. Now, because that's memory mapped I/O, some I/O device might actually be changing some value. So there may be some other external actor in the system that the compiler doesn't have any knowledge of. So what we use volatile to say, hey, I know what I'm doing, don't get rid of this variable. So that's kind of a use case for volatile. But that's going to go ahead and do it for this example. So we looked at what the static keyword means and how that relates to having persistence between function calls or between objects. We talked about mutable and constant, how they work together, and how you can use mutable to kind of get past some of the rules that constant has. And then we talked about volatile and its effects on our compiled code. But that's going to go ahead and do it for today. Feel free to check out all my stuff at github.com/coffeebeforearch. So I've got all the code for all my series here. So we looked at C++ Crash Course today, and I've got links to all the videos as well as links to all the code used in the videos. So we looked at Modifier Deep Dive today. So feel free to download this and play around with it, and let me know if you have any questions. And as always, I'm Nick, and I hope you have a nice day.